Hello viewers, for the last two programs we had seen the VI characteristics of two important thyristors. One was the silicon control rectifier, that is SCR, and the other was DIAC. In this program we are going to verify the VI characteristic of another important thyristor called the TRIAC. For verifying the VI characteristic of TRIAC we are going to use this setup which is before you. But before I take up the experimental part, let me explain a little bit of relevant theory regarding TRIAC. Now TRIAC, DIAC and SCR, all these three are 4-layer semiconductor devices. If you see a little bit of difference between the three, you will find that the TRIAC has three terminals known as main terminal 1, which is MT1, main terminal 2, MT2, and gate. The DIAC has only two terminals, main terminal 1 and main terminal 2. There is no gate here. And in case of TRIAC, sorry SCR, you again have three terminals, anode, cathode, gate. Now if you compare the two, TRIAC and SCR, you will find both have three terminals, MT1, MT2, gate in this case, and SCR, anode, cathode, gate. So you find that gate is common between the two, and you know that gate is meant for control. So both these devices, that is SCR and TRIAC, are control agents. They are also known as control devices. But in case of DIAC, you will find only two terminals are there, main terminal 1 and main terminal 2, and this is meant for triggering either SCR or TRIAC. This is known as triggering agent. Why triggering? Because there is no gate here. So this is only for triggering either SCR or TRIAC. Now if I draw the symbolic representations, first the TRIAC will look like this, and you will find two arrows. The terminals are like this, and there is a third terminal here. This is main terminal 1, this is main terminal 2, and this is gate, because this is TRIAC. If I draw the DIAC, it will also look like this. That means two arrows, the terminals are one here, one here. This is main terminal 1, this is main terminal 2. There is no gate here, and the SCR will look like this. Only one arrow. Here another terminal. So terminals are anode, cathode, and gate. This is of course DIAC, and this is SCR. Now let us see what are the differences. If I compare the TRIAC and the DIAC, you will find the two arrows are there in both the cases. That means both these devices are bidirectional devices, and both of them can conduct either from MT1 to MT2 or from MT2 to MT1, the TRIAC and DIAC both. And in case of DIAC, you do not have a gate, here you have a gate. But in case of SCR, you will find that this only conducts in one direction. So one arrow is here, and the conduction state, the current will flow from anode to cathode only, and the condition you remember for conduct of SCR, that it has to be forward biased. So, constructional point of view, if you compare TRIAC and SCR, they look alike because there are 3 terminals here also and there are 3 terminals here also, and both are control agents because both have gates. But operation point of view, if you compare, the TRIAC and the DIAC are bidirectional devices, whereas SCR is a unidirectional device. Now, this is the difference if you draw the symbolic representation of the 3. Let us try to understand the layer diagram of a TRIAC. You remember, the layer diagram is very, very important because it tells you in detail the construction of any device. And you will find here that the TRIAC is also a 4-layer semiconductor device. Let me draw the diagram for you. The diagram will look like this. You will have one layer here, another layer. So, this is P, this is N, this is again P. You have 2 small n layers like this, one n here, one n here, and another n here. The terminals will come out like this, one here, one here, and one terminal will come out like this. So, the terminals are MT1, G and MT2. Now, you find that there are 2 P layers here, 1 N layer here and 3 small N layers. These 3 small N layers will form another big N layer. So, in all there will be 2 P layers and 2 N layers. So, it becomes a P N type of 4-layer semiconductor device. So, this is all about the layer diagram of a TRIAC. Now, let me draw the VI characteristic. If I draw the VI characteristic, of course, this is V, this is sorry not V, this will be I, that is current, this will be I and this will be V. Of course, this is minus V, this is minus I. The characteristic will look like this, it will go like this, like this. Here also will come like this. So, what is happening here? I will explain. This is the first quadrant characteristic, this is the third quadrant characteristic. In the first quadrant characteristic, you find that in the beginning there is very little amount of current flowing till this point, and this point is known as VBO, of course positive. Suddenly the device triggers and there is a heavy inrush of current. That means at VBO the device after triggering starts conducting and there is a heavy inrush of current, but correspondingly the voltage, which is say V dash, goes very, very small. So, this is first quadrant characteristic. In the third quadrant characteristic also, in the beginning there is very small amount of current till this point, which is say minus VBO, and here at minus VBO suddenly the device triggers, starts conducting and there is a heavy inrush of current, but correspondingly again the voltage, which is say V double dash, goes very, very small. So, I will repeat, in the first quadrant characteristic, in the beginning there is very small amount of current flowing till this point, and this current is known as leakage current. At VBO the device triggers, starts conducting, there is a heavy inrush of current and the corresponding voltage V dash goes very, very low. In the third quadrant characteristic also, from this point to this point, which is minus VBO, there is very small amount of current flow, which is again known as leakage current. And at this point, that is minus VBO, the device triggers, there is a sudden inrush of current, that means starts conducting, and correspondingly the voltage V double dash goes very, very low. So this is the VI characteristic of a triac, and again you see that the first quadrant and the third quadrant characteristics, they look alike, there is no difference. So the same characteristic is going to be verified with the help of this setup which is before you. So now I am going to take up the experimental part. This is the main board on which I have rigged up a simple circuit for verifying the VI characteristic of triac. This is the triac which has got 3 terminals, this is G, this is T2 or MT2, and this is MT1. Now there are a lot of terminals you see, these are the 2 terminals, they are meant for a power supply which is to be given across the triac. This power supply is to be obtained by this supply, and it is positive here, negative here. It is clearly shown here 0 to 35 volts. So I will vary a voltage from 0 to 35 volt across these 2 terminals. Now these 2 terminals are also meant for a voltmeter reading, and here this is the positive, this is the negative terminal, and this is meant for noting down the voltage across the device after it triggers. Again these 2 terminals, this is positive, this is negative, they are meant for another voltmeter, and here a voltmeter will be connected for noting down the voltage at the gate of the device. Now these 2 terminals, you find that this is positive, this is negative, and this is meant, these 2 are meant for an ammeter. We are going to connect an ammeter between these 2 to note down the gate current. This is again a positive 10 volt, it is written here. So this is meant for a positive 10 volt supply, and this voltage is obtained by this power supply, and this is to be given at the gate of the device, that is triac. These are the 2 terminals, this is positive, this is negative. Here again we are going to connect ammeter. So this analog multimeter which is going to be used as an ammeter will be connected across these 2 terminals. Of course this is the positive, this is the negative. Now for these 2 terminals I am going to use this yellow one, which is nothing but a digital multimeter, as a voltmeter. For these 2 terminals, this black one, which is again a digital multimeter, will be used as a voltmeter. For these 2 terminals, again this black one, which is a digital multimeter, will be used as an ammeter. And across these 2 terminals I am going to use this analog multimeter as ammeter. Purposely I am doing so because I have to note down the current across the device when it triggers, and right at that moment you will find a chute in this multimeter. So this is all about the circuitry. Of course this is the potentiometer. By varying this I will vary the gate current, and at a particular value of gate current this triac is going to trigger and it starts conducting. This is of course a 5 ohm 5 watt resistor which will act as a load resistor and to bear the total current in the circuitry. Now I will connect the experiment for you. So this is the power supply, the positive will come here, the red will go to the positive, and the blue one will go to the negative terminal. So the power supply is connected here, then these voltmeters, of course this positive will be connected the red terminal, the negative will be connected at the black terminal. This multimeter also is to be connected like a voltmeter. So this red will go here and the blue will go at the negative terminal, and this will be connected as an ammeter. So the positive will come here and the negative will go at this terminal. So all these 3 meters are connected, this power supply is connected. Now I will connect this plus 10 volt supply which is here. Yes, this will be connected at the plus 10 volt which I am going to get from this power supply, and now these two terminals, the ammeter as the positive will come here and the negative will come here. So the connections are all over. Let me tighten the connections, and now I will first of all switch on the power supplies. So both the power supplies are switched on. I will put on the multimeters also. Now I am going to repeat what is happening here. This power supply is connected here for 0 to 35 volts supply. This power supply is connected here for plus 10 volt constant. This multimeter is connected between these two terminals, across these two terminals, for noting down the voltage across the device. This multimeter again as a voltmeter for getting the gate voltage, and this multimeter between these two terminals to note down the gate current. This is of course in the original position, the potentiometer. It is a 100K potentiometer, and now I will fix up the voltages. So let me first of all fix 10 volts here and 10 volts here. Now the voltages are fixed. Now I am going to adjust the potentiometer. Actually I am going to increase the gate current here. So I am gradually increasing it. You see the gate voltage is changing, the gate current will also, yes, it is also changing, and you have to concentrate on this multimeter, because at the time the device triggers it will give you a shoot. Okay, I am increasing it further. Here you see it has given a shoot, that means this track has triggered. Now let me note down the voltages and currents also. For that I would like to use my specs. You see first the current. The maximum value of current is 1 ampere exactly. It is 1 ampere, and the voltage here has come down to 1.42 volts. This is the voltage across the device when it has triggered, and the current is 4.7 milliamperes. I will note down the values. Voltage across track is equal to 1.42 volts. Gate current is equal to 4.7 milliamperes. The maximum current across the device is 1 ampere, that is 1000 milliamperes, and of course these are the gate current, maximum current, and the voltage across the track. Now let me change the voltages here. For that let me explain here first what are the readings you have got. You have got this, of course this is the original. This value is 10 volts, this maximum current is 1 ampere, you noted down, and corresponding V dash is 1.45 volts. So you know this point, you know this point, you know this point, and you know this point also. So this part of the characteristic, that is the first quadrant characteristic, can be plotted. But if you have some of these points also on this line, then it is easily plotted. For getting these points, what I am going to do is I will change the voltage in steps and note down the values of the current. Okay, let me do it. For that I am not going to disturb the potentiometer. I am going to make it 0 volts, and I am going to change the voltage in steps. Okay, let me see. Okay, this is 2 volts, and the current is 100 milliamps. 2 volts, note down the values, voltage, current in milliamps, 2 volts, 100 milliamps. Further I make it 3 volts, and it is 100, 200, 300 milliamps. 3 volts is 300 milliamps. Then I further make it, increase it rather, to 4 volts, and the current is 0.5, that is 500 milliamps. Then I make it 5 volts. 5 volts, the current is 650. 5 volts, 650 milliamperes. Then I further change it, say 7 volts, not 7 exactly, this is 6.5 volts. Okay, 6.5 volts corresponds to 900 milliamperes. And next, if I increase, it has conducted. So I will take only 1, 2, 3, 4, 5 readings. Okay, so 2 volts, 3 volts, 4 volts, 5 volts, and 6.5 volts. Okay, so I'll note down the values for you. Let me write down the values. Because the original values will be maximum current that was equal to 1 ampere, gate current was equal to 4.7 milliamperes, and the voltage across the triac when triggered was equal to 1.42 volts, right. These were the original readings, and now the voltage and current. So this is voltage, this is current, of course in volts, and this is in milliamps. The readings are 2 corresponds to 100 milliamps, 3 corresponds to 300, 4 500, 5 650, and 6.5 the current is 900. Okay, I will repeat. The maximum current across the device when it is triggered is 1 ampere. The gate current corresponding was 4.7 milliamperes. Voltage across the track when it triggered was 1.42 volts. And the step, as I change the voltage in steps, 2 volts corresponds to 100 milliamperes, 300 milliamperes, 4 volts to 500, 5 volts to 650, and 6.5 volts to 900 milliamperes. So with these readings corresponding voltage and current, I can plot some of the characteristics here, and I know this point, I know this point, I know this point, I know this point. So I can very easily plot the whole first quadrant characteristic. So this is about the first quadrant characteristic. Now if I have to draw the third quadrant characteristic, that is the second part of the characteristic, what do I have to do is we have to give a minus voltage supply here. Okay, for that what we are going to do is, for minus voltage we are going to interchange these two terminals. We can interchange, that is the positive which is coming here will come here, and the negative terminal will be connected here. Similarly this multimeter, that is the ammeter, will have to be interchanged. The positive terminal which is right now connected will be connected here, and the negative will come here. Rest of the connections will remain same, and then we have to repeat this experiment as we did it for the first quadrant. Again take down the readings, again take down the voltage versus current readings, and then plot the third quadrant characteristic. Now if you do so, you will find both the first and the third quadrant characteristics are absolutely alike. Now so far we have drawn only one set of VI characteristic for a track. We can draw many such set of characteristics by varying this voltage which we are getting from this power supply. We can vary from 0 to 35 volt. In this case we had given 10 volts here, but I can change it to 15, 20, 30 and so on. So I can vary the voltage here and I can plot many such characteristics. At every step you will find the VI characteristic of first quadrant and the third quadrant will be absolutely alike. So friends, this verifies the VI characteristic of a triac. In the next program we are going to see the VI characteristic of another important semiconductor device known as the UJT, that is uni-junction transistor. Thank you.